if I...
This meeting is being recorded.
If I... Let's see... Oops. See if that works. All right. Bring up the schedule. Then we're on to week 4. We have the chapter 1 homework due Wednesday. Is that right? Yes. All right. So it's a bit later than my other 2 courses. So I may have got some. All right. So any questions about the chapter 1 homework or appendix? All right, the 3 questions from the end of the chapter, and then the, oops, I don't know why that's happening. And then the sum of products and the simplified expression. Okay. So today we're going to dive into chapter 2, and we'll be working on that this week and next week. So in chapter 1 in appendix A, we sort of lay down the foundations, the groundwork of how our computers are built, or in particular our CPUs, and how they're organized in the sense that they're built up from silicon, rather than wood or paper. And they're organized into transistors, and then organized into logic, represented by Boolean algebra. And from there, we've got the other components of our computer. So one of the things we need to do is then we'll look at, in chapter 2, the instructions of the computer. Chapter 3, how the computer does math. And then chapter 4, we'll connect appendix A and chapter 2, because we'll sit there and say, now that we've got these instructions, how are they processed inside the CPU at a layer above just the individual logic circuits, right? And then those logic circuits will be invoked as part of chapter 4. Okay, so we're just doing, like I said, chapter 2, and the slides are, of course, available under the link. And so the instructions, the language of the computer, right? So what we're looking at and what we're going to focus on in this chapter is the instruction set. Different computers have different instruction sets, but they have some common elements. They started out with a simple instruction set. ENIAC basically just did a few math operations. Everything was fed in externally and processed back out again. And what you'll find is there's actually a common core set of instructions that need to be done by any computer, and then you'll see some variation in some of the optimizations that are done, and also in the wide range of extra types of instructions to help facilitate performance, right? You'll also see variations on a theme across the instructions, right? So rather than have an instruction with some arguments to modify the behavior of that instruction, what you end up having is, for performance's benefit, a bunch of different instructions that all do something slightly different. And then you do the appropriate instruction for the slightly different thing. So the current ARM instruction set is actually version 9. So the book is one level behind. But version 9 really focused more on performance and security features over version 8. So not really an overhaul or change of the instructions, and those have remained pretty stable across the various versions of the instruction set. So the company that owns it is called ARM. Originally, that wasn't just a single word. That was an acronym for Acorn RISC Machines, right? And originally they did something slightly different than license out the design to other companies, and then other companies would, like Apple and Samsung, would have the chips manufactured following this design. Historically, the ARM architecture has been very low power is one of its features. And so it quickly grabbed first the embedded market, because it was relatively cheap to license also, and then the phone market, right? And so there's a reference card, the PDF, that'll be under, let me show you where that is. So under the course documents, there's also the green card. It's green in the physical textbook. It's white PDF here. So we'll get to it in a minute or during this chapter, right? But what I wanted to do real quick is do a little bit of historical background for the ARM architecture. So under course resources, CPUs, I found this great article by Ars Technica, and they started out in 1983, and the IBM PC came out in 1981, so that's the time frame of this right there. And so the IBM PC had a 16-bit x86 processor at the time, and they had moved from an 8-bit processor originally for Intel with the 8000 series chips. And then eventually they would move to 32 bits and 64 bits. So the first ARM was starting at 32 bits, so they skipped the 8 and 16-bit levels, but Acorn Computers was using a 16-bit processor, and they wanted to move to a new processor, and rather than buy a new processor, which they were unsatisfied with the current range of 16 or 32-bit chips that were out there, they decided they did have a background in doing some design work on their graphics and their input and output chips, so they decided to build their own chip. And a two-person design team, Sophie Wilson, Steve Ferber, and then a few other people to help with the layout and different components. And what they built was a chip. And if you want to read the rest of the article, knock yourself out. It has some good illustrations in it, demonstration of an AND and an OR gate, of an adder, and there's an interactive version there. Maybe we can visit that for chapter 3. But for today, what we looked at is version 1. And so what they were looking for was high performance. And one of the things they had managed to do was their previous chip. It was the 6502, which was built and designed by somebody else. But they had managed to pair it with fast memory and get better performance than other people were getting with the chip. And so they wanted to do something like that. So what we can see is the other thing they did is they came across a paper by Berkeley talking about this new way to organize the instructions called the Reduced Instruction Set Architecture, or RISC. The idea here is that the instructions are simple and reduced in the sense that they do less work per instruction. So if we take a look, universally, all of these instructions are completing in a single clock cycle. And they have very few. So there are some broad categories for the instructions. So if we take a look, we need to move instructions around. I wonder if I can hide that ad temporarily. We'll do that so it won't blink as much. All right. Actually, I think I can just do that. All right. So we have some instructions to move data around. That's the move and the load and the store. So the first 6 rows. Then, of course, we need to do some math. So we've got addition, subtraction. We've got the logical operations from our gates, right? So we've got and, or, exclusive or, a bit clear, and a few other math operations, reverse, subtract. So that's good. And then the other thing we need to do is support in a higher level language, or even in our assembly code, a way to move around in our program. So we've got 3 different main things that we want to do. We want to do loops. So that means I have to choose between keeping in the loop or exiting the loop. I need to make a decision, so if-else logic. And I would like to also jump around in the code so I can define modules, procedures, functions, right? And so I can modularize or block out and make my code in a procedural manner. So we need some comparison operations and also some just unconditional branching where I just say I need to go somewhere else. And so we've got those covered. And then the last thing that we need, and we'll talk about this again near the very end of actually chapter 4. We won't really talk about it as much here in chapter 2. But you also need a way to have the CPU get notified by the rest of the system that the rest of the system needs to talk to the CPU. By that I mean things such as the network card, the mouse, the keyboard, any other kind of I/O stuff. And typically the mechanism to do that is what's called an interrupt-driven system. So there's support for that too. So versus, in this case, the Ars Technica is a little bit shady in that they're comparing it here to these 45 instructions to the 350 instructions of the x86. But at this point, the x86 is around 3 generations old. So the original very first x86 instruction set was around 100 instructions, right? And at this point, it had grown to 357, right? And the current ARM instruction set and x86 instruction sets are both around 1,000 instructions now. So they're both grown over the last 40 years or so from when this was true. Now, the difference between RISC and CISC originally, it's kind of blurred by this point in time, is I think illustrated well by this diagram. So the idea in RISC is I could focus on making each of my instructions execute as fast as possible if I keep them simple. So while this would look like that I might be taking 4 times as long, I'm actually doing the same amount of work on both sides. The difference in the CISC is the instruction is more powerful. The reason for this is some trade-offs. So the trade-off is that memory was very expensive for the early CPUs, and memory prices started dropping, and that's where Berkeley and the RISC crowd came into play. But so the idea is the instruction on the left takes up less memory to store it, whereas I have to store 4 instructions on the right. However, what I can do is with my simpler instructions, I can run the clock rate of my machine vastly higher. So the RISC machine, these early RISC machines ran at a way higher clock rate than the CISC machines, and so they had comparable or higher or better performance, right? But the idea was to multiply on the CISC side is it's actually referencing 0A and 1F memory locations. So it's getting the value from memory, putting it in the CPU, doing the multiplication, and then storing it back out again. So this one multiply operation still has to have the circuits, the logic, to implement all of these 4 instructions, which therefore means this will take up more time to do, and so likely is not completing at the same rate of each of these individual instructions. So more likely I can run the RISC machine 10 times faster and get a much better performance. This also had other implications that we'll talk more about in Chapter 4 for then how we could organize the CPU to gain even better performance. But in short, the technique would be called pipelining. And so the CISC didn't lend itself to that, whereas the RISC did. Okay, so a little bit of background there, and some of it will become clearer as we spend more time with the material. So instructions. Well, let's start off simple. Remember, at the end of Appendix A, we talked about arithmetic logic unit doing addition, negation, a bunch of logical operations. And so addition is something we want to do. So if I'm going to add two numbers and get a third number, the result, then I need an operator. That's our addition. And I'll need 3 operands, A, B, and C, 2 sources and a destination. And how these are organized will depend from architecture to architecture and documentation to documentation. And so instead of having to describe all this with zeros and ones, which I will show a bit later, we would like to use a mnemonic. So we'll just use the word add. We'll keep it short so we don't have to write that much out on our piece of paper or in our text editor. So we're going to have a regular semantics or form to each of our instructions. This also helps on the Chapter 4, the CPU side, was decoding the instructions. So what happens is, back in the 50s, we moved from individually programming the zeros, the bits ourselves, to having a mnemonic. So we had to have an assembler to assemble our adds and subtracts and stuff into the machine code. And then in the 60s, we added a compiler to it. So high-level languages. This is much easier for us to read. F equals G plus H minus I plus J. Plus, we can use meaningful names here, though I guess F, G, H, I, and J is not that meaningful, but I mean, it could be meaningful. So here, I don't have an instruction that does addition and subtraction and addition all at the same time. So what I do is I break the C statement down into individual instructions. And so I've got 2 additions and a subtraction. And what we'll also see here, that instead of having just 5 variables or 5 memory locations, I now need 7, right? 1, 2, 3, 4, 5, 6. 7 memory locations, because I temporarily need to hold the results of the 2 additions before I can subtract one from the other. Now, this is actually not completely accurate. In the RISC architecture and in the CISC architecture, for performance reasons, what you want to do is have the data items as close as possible to the CPU. The closest way you can get them to the CPU is to store it in the CPU. So the CPU will have registers, right? So individual memory locations. The modern ARM architecture actually has a lot of registers, but the general purpose registers, there's 32. The original version 1 started with half that many, 16, 15 plus 1 for a dedicated special purpose. And that's actually true here, 31 plus a read-only 1. So, and the original version 1 had 16 general purpose registers that were 32 bits. Now we've doubled that to 32 64-bit general purpose registers. So 32 bits is a word, 64 bits is a double word. If we're referencing the entire register, the author is going to use X. And if we're just doing the first word, we'll use W, right? And so we can either put a 32-bit integer or a float in there, or we can put a double, right? And this is in the CPU directly. Notice the difference in the numbers, right? Versus, the 32 gigabytes of memory that you might have for your computer. This is a billion less locations. But we don't need to access all billion locations at any one time in the CPU. So this is sufficient for our purposes inside the CPU. So we're going to break it down. And so, fortunately for us, unless you're writing assembly code, the compiler/assembler will take care of all of these. We will revisit X0 through X7 when we talk about function calls in more depth. X8, we'll let the assembler take care of that one, so don't worry about that. X9 through X15 are intended to be temporaries. We can also use 16 through 18 for temporaries, or the compiler assembler might use them for other purposes. Depends on who's writing the code, the compiler or you, the programmer. 19 through 27 need to be saved, and we'll talk about the difference between temporary and saved in a little bit. And then the last 4 registers are special registers. So they're always used for these purposes. We won't use them as sort of general data registers as we're doing for 0 through 27. 28 is the stack pointer. We'll talk more about the stack pointer, but basically if I need more space than the 32 registers give me, I can use the stack. And so I need to point to that because that's actually in memory. And so that is pointed to by the stack pointer. The frame pointer is pointing to where we are in the code. It's used for function calls in part. The same thing with X30. When I do a jump to some function or procedural code, then I need to come back to my original calling code. And X30, or the link register, is the return address to get back from my function call. And then the value of 0 is useful enough that we can pull it from somewhere. What we're going to do is pull it from register 31. And so register 31 can't be written to either. So what we can use it as is a dummy register in some instructions where we tell it we're putting something there, but we know that's not actually going to happen because register 31 is read only, and so it will not be modified. So, like I said, this example is not 100% accurate. So what should it really look like? What it should look like in a RISC architecture is that all of the operations will be dealing with registers. And therefore, I need to have all of the variables copied to a register. So we'll have had in this case, we will have needed to have 5 load instructions before this addition to load registers 19 through 23 with the contents of F through J. Then what we're thinking about as a higher level programmer are actual math statement, the 3 instructions. And so we can also see the authors using 20 through 23 as saved registers. So those are more permanent in the execution of the code or more persistent, whereas we can expect X9 through X15 as temporaries. So the temporary values for the addition will hold in a temporary register and immediately be able to discard or ignore them and overwrite them in the next block of code. And then we'll put x19 in representing F. So in this case, G, H, I, and J don't change, but F does. So I would need 5 load instructions, the 3 math instructions, and then a store instruction to store the results of x19 back out to F to be completely accurate. Now, main memory is where we'll hold all our data and our instructions, and we'll get more about how that's organized a little bit later in the chapter. How that data is organized, we can have individual items, right? So individual values such as F, G, H, I, and J, which I'm going to assume are all integers and probably 32-bit integers, maybe 64-bit. But arrays will be blocks of sequential memory designated for the arrays and done in that manner to facilitate accessing the elements of the array. There will be structures such as records or objects, however you organize it in your higher level programming language. And then if you use something like dynamic object creation or the new keyword in Java, C, and in other languages, or in some high-level languages, you might not explicitly use new to create a new memory location, but the interpreter running the language will do that for you, right? So that's dynamic data. So in a RISC architecture, we'll load the values from memory to register, do the math, and then we'll store the result back out from the register to memory. We don't go down to individual bits, so we'll do what's called byte addressable memory. And depending on the compiler and the architecture and things like that, you may sit there and say that that memory has to be aligned on boundaries that are, byte alignments or word alignments. In this case, there is some alignment for the architecture for instructions in the stack, but not necessarily memory. So how does an array work? Well, an array, if you remember in C, if I sit there and point to an array, like declare an array, like int my array 10, I'll type that in the chat window as an example. All right, and if I was being cautious, maybe I would initialize it depending on the syntax and the version and stuff like that. So my array in C code is really just a pointer to the memory location of the first element in the array, which is at index 0, right? Remember, we're using a 0-based offset. So if I'm looking at A12 and A8, what I'll do is the pointer will be stored, its address is in x22 in this example, and this can change from program to program. H is some singular value, its value is in x21. Those are persistent locations, so we'll use those save registers. Now, to get the 8, the problem is we just write index, right? So this is 8 locations off, 12 locations off. But the compiler needs more information, right? The assembler needs more information. So the compiler will look at the data type and say, oh, each element is actually this big, and so let me scale that. So 8 is, in this case, we're looking at 64-bit data. And remember, we're doing byte addressable. So 8 times 8 will give us an offset of 64 bytes. 8 times 12 will give us an offset of 96 bytes. We start at the base address. This syntax will say, give me the base address plus 64 bytes. Give me the element at that location, and I'm going to load it into a register X9. I've got H and X21. I'll put them back in X9 because I'm going to replace X9. I used a temporary. And the result of the addition, I'm going to write immediately back out to the array. And I'm done. And I'm ready to move on to the next block of code. So any questions on that syntax or what happened here? We're going to see this a lot. So make sure that you understand what's going on here. All right. Oops. So even today, memory is slower than the registers because memory is located away from CPU, and typically memory is on a different part of the computer, so it runs at a different clock speed, and it's made at a different scale, and maybe even different manufacturing process, so it's slower. So rather than deal directly with memory, a RISC-based architecture and really a modern architecture will transfer the data through the cache system, and we'll talk in that in depth in chapter 5, and from the cache system to the registers. So this is, again, another reason for us to do high-level code and not do assembly code ourselves. This assembler will take care of doing register optimization. We have a small number of registers, and the assembler will be able to scan through the code, figure out how many registers it needs for that block of code, and optimize their use so that we don't have to keep moving stuff from the registers to the stack or back to memory while we're executing our code. So one thing that we could do is, if one of the values is small, rather than load, and we know that the value is a constant, rather than store that constant in memory and then have to load it and use it, we might have a slight variation on our add instruction, add immediate, and save ourselves a register location. Instead of 3 registers, I can use 2 registers, and you can see the optimization here is that we're overriding the old value as a new value. So something like x equals x plus 1, or in this case, x equals x plus 4. And so in this case, we've gotten ourselves down to 1 register instead of 3 registers. Because what we'll do is, in place of the 3rd register, we will use part of the instruction itself to hold the small value, and it's got to be an integer, a small constant integer. So we'll avoid a load instruction, faster all around. All right, so before we move forward, we'll talk about numbers in more depth in chapter 3, but we'll talk a tiny bit about numbers in chapter 2, because in this case, we're doing general purpose operations, which do include integer operations, since we use integers for arrays, indexing, and for loops, right? And so it's useful to have an understanding where they are. For our integers, we've got unsigned integers. In a 32-bit system, 4 billion values. In a 64-bit system, a lot more values, zeros and ones. This one's pretty straightforward. I don't need to use any of the bits for anything but holding the number. If, on the other hand, I want to have negative values, then I need to maintain that signed value. And so there are a number of different ways, but what modern computers use is a 2's complement. If you look in the textbook, there's a page where they describe some of the earlier versions. So there's 2's complement, 1's complement, and sign and magnitude. Let me see. That constant here is going to be stored inside the instruction itself. So when I show you the format of the instructions, there will be a space in that format to store small constants. That'll be in the I format instruction. Whereas the regular instruction will instead reference the what register value IDs are being used. So we don't need to store it in a CPU register. It can actually be decoded from the instruction and sent directly to the arithmetic logic unit. And that part will become more clear in chapter 4. Now, did that answer your question? All right. So back to 2's complement. So sign and magnitude is the way you would think about it. I have a sign bit and the magnitude. For various performance reasons, 2's complement wins out over 1's complement and sign in magnitude. What we'll see from 2's complement is that I will have the number, in this case 4, and if it's a negative value, every bit beyond the number will be filled in as a 1. And you can still look, for testing purposes, to do things very quickly, you can still look at the largest bit and see if it's 0 or 1. If it's 1, it's a negative number. If it's 0, it's a positive number. So if you're just doing a quick test to see if the number's above or below 0, you do this. If you need to actually compare the values, then you would have to decode the number. So 0 will be all zeros. Negative 1 will be all ones. The most negative number will be all zeros with a single, the high order bit 31 as a 1. The most positive number will have all the bits filled in as a 1, but the leading 31st bit will be a 0. So to get to 2's complement, take a positive number, flip all the bits, complement all the bits, and then add 1 to it. And that's the easy way to then find out what the negative value is, rather than try to decode it back. It gets a bit difficult. So if I have positive 2, they're all leading zeros, and here is 1, 2. So here's 2. I flip all the bits and add 1 to it. I now have a negative 2. But the real secret here is just let the compiler and the assembler take care of all this for us. One of the benefits of this system is if I have a smaller number in number of bits, right? So like a 16-bit value, or in this case an 8-bit value going to 16 bits, then it's easier for the computer hardware to go, you want me to fit this small number in a larger space? Well, the problem is, what do I put in those other bits? And so I can do assign extension instruction where I load a small number of bits and extend them out to fill a larger number of bits. And if the leading bits of that smaller sequence of bits is a 0, I'll extend it 0. If it's a 1, I'll extend it 1. As we see here with the light gray values versus the black values. From the 8-bit to the 16-bit. From the 8-bit to the 16-bit. There's also just a 0 extend. I don't care, or I know I'm extending an unsigned integer. I'll just use a 0 extension. So the appropriate instruction to use is dependent on the context, right? So the compiler will take care of determining that, unless you're writing the code yourself. So, to get back what was asked about, we will look at the mnemonic or the small text description, but that is not suitable for the computer. So in chapter 4, you need to load in the machine code. Now, one of the other characteristics of this RISC architecture, the ARM architecture, is they fix the size of the instruction. So they don't have variable length instructions. A contrasting architecture is Intel, where Intel has varying length instructions, which was done to save storage, but then adds an extra complexity that you have to decode the instructions in order to figure out how big the instruction is before you can even start processing. Here, the idea is every single instruction is the same size. So I go into memory, grab 4 bytes. I have one instruction. I decode it and execute it very fast. Now, 32 bits is 4 billion possible combinations. So I need to reduce that. And so I'm going to have a small number of formats that I can use for my decoding purposes, and gives me a regular format. Now, with 32 bits, that is 32 zeros and ones, which is represented at the bottom of the screen here. 1, 2, 3, 4, 5, 6, 7, 8. So I can't really read 32 bits easily. So even here, what you'll see people commonly do is they'll put a space between every 4 bits, because every 4 bits can be more compactly described as a hexadecimal digit. And so the 4 bits can be 0 through F, right? Where A, B, C, D, E, F are 10, 11, 12, 13, 14, 15. So this ends up being base 16, 0 to 15 value, and it's equivalent. It's just a sort of a higher representation of our binary encoding. And so I can describe these 32 bits, or these 32 digits, as these divide by 4, 8 hexadecimal digits, right? So 1110 is E, CA86420. So what you'll typically see in tools that look at the binary code, those are called like binary editors, or really hex editors, because they'll show the values in hex format. I normally do give an example here. The binary remains the same, right? So the number, the actual value is unchanged between whatever representation it is. So I'm on a Mac, and I have a tool called HexFiend. So when I open it, it looks like that, untitled, and it doesn't show much. So what I'll do is I'll browse in and open up a executable code. And you get something like this. So in this case, I opened up Chapter 9 array list. This is for my Fundamentals 3 course, which I haven't taught in a while. And so here you go. On the left is the zeros and ones, but rather than show them all, what we'll do is translate it or represent it in hexadecimal format. And so this is the entire program has been loaded. This is actually not a big program. It's 60,000 bytes. And so I can load it all in. Interesting enough, if there are like character strings encoded in this C code, you will, let's see if I can find any. Yeah. You can see the text representation of the hexadecimal. This is sort of a dumbified translation of the hex code into ASCII code. And so it doesn't always work. And so we can see it's not really working here on the right side. But here we can see that this binary data here actually represents some text data, so a text string of some kind for error messages. And then these are all zeros, so nothing shows up here, it's all blank. And so it looks like there's a large chunk of zeros, depending on how this executable has been partitioned or broken up into sections. You can easily find many such hex editors for free for whatever operating system you're interested in. Oops. Okay, so let's talk formats. Said we want to have a handful of formats, and I'll show you. It's in the PDF. The green card PDF has a list of all of them, and they're listed somewhere in the textbook too, and of course ARM's website. So here we go. For an R format, I like to use R as a short for arithmetic logic. Organizational wise, the relevant thing is I have 3 registers. 2 source and a destination. 11 bits gives us, 2,000 possible combinations for an opcode. With 32 registers, I need 5 bits for the ID of the register. And I can, therefore 11 plus 15 gives me 26 out of 32. That gives me 6 left over, which works perfectly, which is the reason we chose 11. 6 bits is 2 to the 6 is 64 locations, or basically the shift amount allows me to sort of look inside the 64 bits of my register, right? And because my register is going to be a 64-bit register in this version of the architecture. So if I was going to do this addition instruction from before, add the contents of X20 and X21 and store them in X9, we can see X9 01001, X20 1, 2, 4, 8, 16. 4 plus 16 is 20. 5 plus 16 is 21. In this case, add doesn't use a shift amount. That's for a logical operation. So this particular instruction in the R format puts zeros in the shift amount. And if we look up this opcode in the tens, 1112, then we would see that this is addition. And here is what the machine encoding is. This is what would be stored in memory for this instruction as part of this program. And if I was to load it up in the hex editor, like I showed you earlier, instead of seeing all these zeros and ones, I would see this sequence of hexadecimal digits. Any questions? So let me show you the green card, and that'll be a good stopping point. So if I take a look under course documents, or it's in the front page of your physical textbook, then I can pull up and his leg is a pun-off arm, and it's also reduced, so it isn't all the instructions. So here we go. Add, the hexadecimal code is 458. Here's the operation. If I go to the second page or the flip side, here's add again. It's an R-type format instruction. The opcode is 11 bits. That's the opcode 1000101110. If I look at the slides, that's the same opcode that they're showing in the slides right here. And then we'll talk about some of the rest of this on next time, but we can also see on here two nice things. Here's a list of the core instructions, and we're going to cover the rest of this chapter. But here's our R format instruction, and there's 5 other formats: ID, B, CB, and IW. For R format, immediate, data, branch, conditional branch, immediate wide. And then here's also the registers from that earlier slide, all listed out here too. So that's a good stopping point for today. Unless you have any questions about the homework, then I will see you on Wednesday.
I've recently been having trouble sleeping. I know. Play a sad song on the world's smallest violin.
So it's my belief that while 90 class cards deliver stupendous performance and should basically run anything, 80 class should offer a more affordable alternative that still delivers the ability to run those super high-end experiences. And to get smoother gameplay, multi-frame generation will obviously be factored in. There's another interesting question to answer too. Nvidia made the claim that RTX 5070 offers 4090 performance, but to what extent can the 5080 do it? That's going to be interesting, right? Because if the 5080 can't do it, what are the chances of the 5070 doing it? Anyway, we've got limited access to Path Trace games in the review period, so I would have loved to have factored in Indiana Jones and Black Myth Wukong, but for now, Cyberpunk and Alan Wake 2 it is. And let's begin with Cyberpunk 2077. In this streaming test, RTX 5080 averages a mere 22.9 frames per second in native 4K rendering with a 75 millisecond latency, which is not great, right? Compare and contrast with 4X multi-frame gen, which averages at 186.5 frames per second with a 50.93 millisecond lag. Switching over from native resolution stats there in the graphing to DLSS performance mode, super resolution, frame rate averages at 61.3 frames per second, a good base point for frame generation with a 36.5 millisecond latency. So there's a 14.4 millisecond hit to input lag in exchange for a 3x increase to fluidity. It's interesting to see that the circa 10 millisecond lag differential on 5090 increases by around 4 milliseconds on 5080. 10 milliseconds plays 14. Kind of makes sense, right? Fewer tensor cores in the 5080 means more latency. The frames take longer to produce. 5080 versus 4090. So here's how that rolls out. DLSS 3X multi-frame gen on 5080 is the closest equivalent to DLSS 2X frame gen on RTX 4090, and it's actually delivering a 15% uplift to frame rate. However, looking at latency, that extra frame rate comes with a 9 millisecond lag penalty. 5080 with 4X MFG offers a 46% higher frame rate versus 2X frame gen on 4090, with the latency deficit increasing to around 11 milliseconds. So with that in mind, I can imagine the 5070 versus 4090 comparison that Nvidia has suggested being like this. I can well imagine that there will be frame rate parity, but latency will be a completely different story. Alan Wake 2 next, benched with the new Nvidia driver that quote-unquote dropped the day before embargo. This does iron out some stutter and also reduce latency in my tests by around 2 milliseconds on average. Still, a 14.25 frames per second average at native 4K with a 239 millisecond latency is obviously totally unplayable. By the time we've maxed out DLSS 4 with 4X MFG and DLSS performance mode super resolution on top, we're at 131 frames per second, practically a 9x frame rate boost, albeit with a heavy 93.9 millisecond latency average. Swapping in super res metrics over native, frame rate hits a 3940 FPS average with a 71.7 millisecond latency average. That's rather high for what is a best case scenario for latency. The difference with 4X MFG turns out to be rather large, 22 milliseconds. This is very noticeable and basically means that these settings aren't really tenable. You're going to need to lower them or reduce resolution. By extension, 4090 comparisons aren't particularly great either. 5080 3X MFG beats 4090's 2X frame gen by around 15% in frame rate terms, which is nice, rising to 46% when we deploy 5080's 4X MFG, which is even nicer. Problem is that frame gen lag here on 4090 is 67.3 milliseconds, which feels heavy, but I guess it's okay for a slower paced game. 3X MFG on 5080 is incurring a 22.7 millisecond latency penalty versus 4090, rising to 26 milliseconds with 4X MFG. So, to cut a long story short, yes, you can achieve higher frame rates on 5080 with multi-frame gen versus 4090 at 2X frame gen. But 4090 is delivering tolerable latency for this kind of game, while for me, 5080 has crossed a threshold. Over 90 milliseconds latency with frame rates well north of 120 frames per second is creating a disconnect that doesn't feel right. My take on it is simple. Multi-frame generation can be great, but tailoring settings to get a good base latency number is required. It also puts into perspective the idea of a 40 to 60 FPS threshold as being acceptable for frame generation. Alan Wake 2 compared to Cyberpunk is proving to me that that isn't really the number that we should be looking at. We need to be looking at having a good base latency before invoking frame generation. And here's the thing, right? As we've proven here, even with frame rates that are relatively similar, every game will have a different base latency. Hello there, and welcome to the latest edition of DF Direct Weekly. And yes, we've done it through a combination of the passing of time and basically turning up every week doing exactly the same thing. We've done it. We've hit our 200th edition. And joining me first questions. We choose the best of all the ones we're best equipped to answer. And we're going to start with this one from the collector. This might be a bonkers request, but for science, hear me out. Have you considered comparing what it would be like to run a game like Cyberpunk at 200 FPS on a 5090 without using any of the AI, adjusting the settings accordingly, and comparing with the 5080 with all the AI trickery, also at 200 FPS, and seeing what the difference is in image quality and input lag? I want to suss out whether AI is as good as all that, or if it's just smoke and mirrors, double question mark. Keeping it classy, blokes, exclamation point. Well, we're still sort of trying to figure out how to fully test MFG, multi-frame generation, in a way that's meaningful. There's been plenty of good stuff out there so far, I think. But absolutely, the concept of targeting a frame rate, although, I don't know, it's certainly a way to compare the impact of MFG, right, Alex?
Yeah, it would. I mean, so there are differences. The one thing is, I don't know if MFGs, I mean, advertising is one thing, but if we're just realistic about what it is doing, we know it cannot possibly be the exact same thing as a natively rendered FPS experience.
Yeah.
It will be different, it'll be worse in input latency, and it'll have a higher propensity for more visual artifacts in certain screen areas or conditions that the game can find itself in. So that test tells us something that we already know from the onset, and it's interesting from an academic perspective, but it doesn't talk about what is the subjective experience of not having it versus having it. And
Right.
I find that more compelling from a use case perspective, because that tells us like a scenario where how many people are going to run Cyberpunk at a native 200 FPS? Or would they rather do something that allows them to play the game the way they couldn't have played it before, with things like path tracing, etc. So, I mean, it's interesting, but once again, like, just fulfilling the academic need to point out something, it's probably very interesting in the form of a video pointing it out, but it's not going to get us anywhere further, especially in like 5 to 10 years when everyone's using MFG. And now we've got this, like, how do we start talking about it then when it's, I was going to say Gang Geba, but like when it's like the thing that everyone's using and everyone has. And like, then how do we start talking about the subjective experience of playing a game? What is our new metric for talking about games at that point in time? And I want to start working towards that direction instead of kind of sitting in the mire of how we would talk about it, versus like super sampling. Like that doesn't bring us much further to a new way to appreciate games. So that's what I want to try and do when we get around to this, and it's going to be coming soon enough. But like, when I talk about MFG, I do want to try and focus the video in a way that hones in on what it is doing actually from a gaming perspective. So yeah, that's the way I'm looking at it.
Thoughts, Oliver?
I mean, just my immediate response to this question is like, if you have a 5080 with ray reconstruction, with reflex, with frame generation, as opposed to a 5090 with none of those features, I mean, I think the 5080 is pretty clearly going to win that comparison in terms of hitting really high frame rates with ray tracing, in terms of looking like really, really good and reasonably responsive there. I think you probably have a great experience. I think it wouldn't be very competitive, but I also think that kind of academic use case is not that important in a title like Cyberpunk, where I think so much of that visual experience is tied up in trying to achieve higher settings using ray reconstruction, using all that AI trickery as this user suggests. I think it's so integral to the experience that comparing it to like a native 200 FPS experience on a 5090, I think that's just a misuse of the hardware. I don't think that's correct.
Yeah, I mean, I think probably a more telling comparison, bearing in mind NVIDIA is trying to tell us that a 5070 is as good as a 4090 in performance terms, is actually to test those particular claims, but it's not going to be. I mean, in the 5080 review, what I did do was to get some input metrics and frame rate metrics together that would compare like 5080 at 3 and 4x MFG versus 4090 at 2x, and the frame rate is higher on the 5080, but also the latency is higher. It's interesting to see the extent to which that matters. I mean, 3x MFG on Cyberpunk was like 16% faster than 2x on 1490, and like 46% faster with 4x. But then you look at the latency metrics, and let's have a look here. Actually, I'm just brought up the page. We're on like essentially 39 milliseconds of latency with that 1490, and then looking at the 5080 with the quote-unquote faster frame rate. Basically, for that 16% of extra frame rates, you're paying 10 milliseconds of latency, but for the 46% of extra frame rate, you're paying 12 milliseconds. So there's an interesting balancing act going on there in terms of smoothness versus fluidity. Anyway, we're going to have a good think about how we're going to approach this particular coverage, because what those metrics don't encompass is image quality, for example. The question is how relevant that image quality is.
No, dude.
Okay, so Grayson killed 2 members and lost us tons of MC mats.
Yeah.
Classic.
I mean, honestly, everyone should come try to get the firebox roll.
No way, he was vibing out, dude. Stunned and I die. Literally the whole pool. No way, he was vibing out, dude. He was vibing out. Did he get stunned? No, dude. No way.
Is he a tank? Is this guy a tank or something? I don't understand. He was vibing out. Wait, where's the rope clip? Wait, so this guy's vibing out.
Stunned and I die. Literally the whole pool. No way, he was vibing out, dude. Stunned and I die. Literally the whole pool.
Oh,
No
wow.
way.
Wait, what the fuck? Wait, this guy was just doing this. So what, he's a healer. This guy's a healer, bro. And he's just moving his head left and right, and he's just not healing the guy. Yeah, so wait, you can see it here. Oh, my bad, you guys probably can't see the clip very well. I mean, this is the best I can do, boys, so this is what it is. Look, okay, so basically the healer is...
Stunned and I die.
Not stunned,
Literally the whole pool.
not using any globals, and then the guy
No
just dies.
way.
And the guy just dies in front of him. Yeah. Dude, kid, too many carbs, bro. Too many carbs. It was a carb overload.
Nicest person, it blows so hard.
Who has the
So-
leather off of Onyxia?
He was, yeah.
I'm gonna crash out.
The leather off of Onyxia.
Huh?
Alright, if you are a melee, warriors, rogues, head to Uber's, fire resist buff.
This is gonna take a while though, because
Okay, I'm waiting for rain buff again. Do you think I'll take
Well, if you're not here in 5 minutes, then fuck you.
Yeah, honestly, if you're not here like right now to get the buff, it's just
we have people waiting for summons still.
Oh, wait a minute.
Okay, I'm logging out.
I don't have my shit boon now. It doesn't matter if I actually need to summon my own
try to
fly.
summon the melee.
I'm spamming almond over a friend. I didn't kill Rhett.
You killed Rat, but so?
No, I didn't. I wasn't eating.
Nah, honestly, I love Rat. It sucks so much, but Retau killed Retau. He didn't Flask of Titans, so.
When you're, 180 frames per second or whatever. Anyway, let's move on to the next question. It's kind of related. This one comes from Michael Giles. Howdy DF crew. A good way to relate relative latency performance to the audience might be to establish a tiered quote-unquote DF latency rating based on millisecond thresholds. For example, sub 40 milliseconds could be great, sub 50 milliseconds could be acceptable, and above 50 milliseconds could be potato. Thoughts? If the 5070 Ti and 4090 have the same path tracing FPS in Cyberpunk, but you're still able to tell me which card actually plays in an acceptable / non-potato manner, then I'll know which card actually fits my needs better. Yeah, Alex.
Wow. I mean, I've seen this. Multiple people have approached me with this idea before. There was a good post about Beyond 3D about it, and I think it's there's merit to it, but not every. So 40 ms will feel great on a mouse. The difference between 40 and 60 ms on a thumbstick-driven controller will feel you may not even notice. So the implement that you're using is really important. Also, the game type is really important. Yeah. Obviously. So it wouldn't be it would have to be some sort of sliding scale that wouldn't actually just objectively say 60 ms is always bad or something like that, because it's a little bit overly specific for the breadth of gaming experiences that exist. So I would need to think about even that.
Yeah,
from my perspective.
I'm just thinking back to your Red Dead Redemption 2 latency video. Where
oh god, it's been a while, but yeah,
some of the numbers that are in there, make frame generation look like a complete non-issue because some of the animation latency there, wasn't it like 400 milliseconds or something crazy?
Yeah, it's ridiculous how a lot of just to do basic stuff he starts it. Most people, it is interesting to talk about. You're talking about 12 milliseconds there difference between on and or between the experiences, and in the grand scheme of things, that is.
They farm tons of mats.
Yeah, we're actually owning.
But
Chance,
it's
I'm
like,
serious, don't G-kick me. I was just trolling. I'm trying to act hard in front of the raid. Please, if you're can hear this, do not G-kick me. I'm sorry, bro. I'm sorry, dude. I'm
beat his ass, Bean. Beat his ass. Tickle him. Tickle his toes. Come on. Get up, Bean, and tickle his toes right now. Come on, take your shoes off and fucking tickle him. Yeah, come on, get it, tickle him. Are you just poking him? Tickle him. For the war chief. That's right.
I'm just remembering
one extra frame of buffered latency in a game. So if you've ever used triple buffering or double buffering at something like 80 FPS, then that's what that would be like. And for the longest period of time, triple buffering was seen as an image quality enhancement in games, not as a detriment. So it is interesting to see how times change. Most people wouldn't be wanting that. So.
I'm enjoying the fact that latency is now in the conversation, but I'm thinking of a particular latency apocalypse, which most people, there was some pickup of the fact, but not exactly wide-scale outrage, which was the move from the PS2 to the PS3 generation, which was latency issues on two counts. First of all, three even. Engines were becoming increasingly more complicated, which meant that the latency was increasing. You had the fact that we were moving from 60 FPS games mostly to 30 FPS games, which is not great for latency. And perhaps most impactful of all was the fact we moved from CRTs to flat panels. So yeah, all of those factors combined, there were some like outrageously high latency scores end to end. But even without end to end latency, factoring out the display, and the display could add like 100 milliseconds of latency, even higher at that point. We were seeing some scores from like Killzone 2 when it was like dropping frames under 30 that were like 200 milliseconds for a 30 FPS or other sub 30 FPS experience. We had the whole Kinect debacle. The latency of Kinect, there was so much going on in that period. I think latency was definitely picked up on with Kinect. But the thing about it is that there was no way to actually give you firm data on latency at that point. And it did sort of come to the fore with Ben Heck's latency controller monitor board, and the Call of Duty guys were all on top of that in getting input lag as low as possible. But yeah, in terms of general conversation, it wasn't really a thing. People just sort of decided whether something felt good to play or not. Yeah, any thoughts, Oliver?
No, I would certainly echo Alex's comments that it depends on the context. I think 40 milliseconds of latency actually would not be that good for a title like Counter-Strike 2. People would be a little bit upset at 40 milliseconds latency, but 40 milliseconds would be great for Civ 7 on a controller, right? It just depends on the context. Yeah. Also, I think a lot of input latency is contingent on things on a controller, especially input response curves and things like that. Camera sensitivity can play into it. I've personally played games that should be operating notionally with very, very low latency, but feel a little bit laggy because the input response curve is not quite tuned as I would like it to be. Or not quite sensitive. But going back historically, titles like Killzone 2 had I think over 200 milliseconds of latency. I think various GTA games like GTA 4, GTA 5 had in the region of 150 milliseconds. That was not too uncommon, I think, on that generation of hardware to have games that were a little bit laggier. So I think it's something that I think in a lot of cases you can get used to it fairly easily. And it's really just those more extreme outliers that do seem a little bit unacceptable, but I still would maintain that a pretty wide range of latency is probably acceptable, especially on a controller for most titles, I would suspect, but certainly less is better.
There could be an interesting point being made for someone like 3D Mark to actually create a latency benchmark, which would be entirely personalized. So you'd have a third-person game, Ooh. You'd have an FPS, all of the different game types, and then essentially. It would increase latency almost on a random basis, and then when it didn't feel good to you, you could actually press a button to say, right, okay, this isn't great.
Wow,
and then,
this is great.
And then you would have a personalized sort of threshold of where input lag matters to you, because that's a bit of a problem. And of course, it would also be controller specific as well, because as you point out, Alex, the mouse is a high precision tool in comparison to the controller, which is basically, and I've said it in the past, like a massive latency sponge. It can absorb a lot of the impact of input lag, and you don't really notice. So yeah, that might be a quite interesting thing to do. Let's move on to the next question. This one from Octolima.
Gotta write that down. Sorry.
Let's move on to the next question from Octolima. If Nintendo maintained a similar level of visual fidelity with better textures and DLSS slapped on top, would that be enough? The artistry really is so strong that I wonder if we may indeed see games DLSS up to 4K despite the cost of doing so, simply because the cost of everything else may well be still quite cheap if they remain at similar levels of fidelity to the Switch, as suggested by the Mario Kart footage. What do you reckon, Oliver? The whole concept of 4K DLSS, we've kind of ruled it out based on the PC side of things, but there could be some sort of lightweight model.
Yeah.
Who knows? What I will say is that whenever I see old Nintendo games emulated up to higher resolutions, they tend to look really, really good regardless.
Right.
Yeah, that's generally my impression as well, and that's kind of what I was thinking when it came to this question, is those Wii U or Switch games indeed in emulators, where you can see those games scale quite well, freed from the image quality and in some cases performance constraints of the original hardware they shipped on. If you look at a title like Breath of the Wild, for instance, that's a classic. Looks great at 4K, there's no need to keep pushing that too hard, but like you mentioned, DLSS at 4K is a very expensive process, it looks like, on this class of hardware. I think it clocked in at like 18 milliseconds in your hypothetical RTX 2050 laptop testing there. So yeah, but I'd also say there's a lot of room for Nintendo to keep pushing out visual fidelity in areas outside of resolution, adopting like more PBR materials, volumetric lighting, better shadows, better draw distances, lots of things they could do in their games. Just having any kind of like temporal anti-aliasing treatment or anti-aliasing treatment in general also is a big thing. A lot of the games do not appear to have anti-aliasing treatment at all on the Switch. That's also even true for Mario Kart 9, it looks like, potentially, so that might be an issue on Switch 2, unfortunately, as well. But yeah, I would expect to see progression in Switch 2 software on a visual level, on a settings level, on a raw visual fidelity level, but I'd also expect to see good progression in terms of image quality, and I would expect that a lot of Switch 1 titles would look pretty great on Switch 2 if only the resolution was increased and anti-aliasing quality was improved. I think that's probably true.
Yeah, it is interesting to note, of course, that with Luigi's Mansion 3, we actually saw Switch 1 actually running pretty advanced stuff, right? So yeah, there is definitely progression from Nintendo, and it's worthwhile for sure based on the quality of that game. Yeah, okay.
Yeah, just I always think about, like, look at the Lego movie that came out years ago, like how perfect that looks, and that's like path trace. Like, it looks like that's like one of my favorite like kiddie kind of movies to point out path tracing in, because it looks like the Lego right themselves, and I find that beautiful. Imagine Mario with that, right? That's cool. So yeah,
good stuff. Okay, next question comes from Sweet Minnie. Close.
Do you have updates on Austin and Mark Williams for today?
Austin will be questionable. Banged his elbow. He's gonna go out and try to give it a go in his warm-ups and shooting, and also have an answer soon. Mark, the trade is still pending, so no answer there.
In an ideal world, would you have everybody available for Monday's game if all goes according to plan, including LeBron and Luka?
I don't know why we wouldn't. We're not trying to hold guys out. Obviously, LeBron just a little bit of increased soreness on that foot after the other night, and Luka. I think is progressing well, but we'll make that decision, in real time on Monday.
And he's been playing well. They won 7-10. We'll be without Miles Turner at center, but what have you seen from them, and what do you think is a piece?
We've got to have a compact shell in transition in the half court. They want to score at the rim. They're the best driving team in basketball. They have shooters, but we can't get caught up in sort of being hugged up on our guys. And some of the second half the other night against Golden State, like, you can't overreact to a contested three. You've got to be able to protect the paint. You can't be.
Sweet Digital Founders, Eurogamer reported that a Sony-backed DMC takedown had been Sony.
Not wrangling people to stay. It's an unrealistic expectation. It just is. I don't like that. Like, a lot of people are going to be harassed by T1 viewers and called roaches and all this other bullshit. It's actually annoying the fuck out of me. Because it's just wrong. And it sucks. I guess maybe Tyler's ego is hurt, and it sucks. He didn't necessarily make a bad call for his perspective and his experience. It's just a lot of stars aligned for him to learn the hard way exactly what is going to happen. Honestly, if we had another Baron situation just like that, the same thing would happen. Even with all this. It doesn't surprise me that people made their call. He says he accepted some responsibility, but I mean, fuck. I see his frustration. It's so close to dying. It's so close. But like, I just don't, he's just not taking a human factor. It's annoying me.
DMCA takedown emitter struck down the Bloodborne BSXD make by Lilith Walther, which had a very nice no-clip documentary and a 60 FPS Bloodborne patch by Lance McDonald. Such a hit was observed with a Nintendo-backed one which struck down any mod having Zelda in its title before announcing the new Zelda game. Do you have hope for a PC port/remake announcement this year, or is this really just IP protection to keep a trademark? I have to say the wonderful progress of Shad PS4 has somewhat scratched that itch for me. I feel like Sony missed the opportunity by waiting so long to sign a new partnership with FROM to make something with this dormant game. Socially distanced hugs and happy 200th exclamation point. I've got to apologise for my reading of that question, but there's so many copyright symbols and trademarks that it actually made passing it quite difficult. But yes, Lance McDonald's 60 FPS patch for Bloodborne, which only ran on debug or rather hacked PlayStation consoles, has been struck down by the quote-unquote DMC takedown emitter. And it's been available for years. Kind of suggests perhaps that Sony is planning something, but at the same time, perhaps the limited availability or application of that patch, owing to the fact that you could only run it on, hacked PlayStation hardware or debug hardware, may have just meant that it didn't, even make Sony's attention. Whereas if you've got millions of PCs able to run Bloodborne at 60 frames per second, that might be a bit more of a problem. But Oliver, this Bloodborne PSX demake stuff, it's looking a bit heavy-handed, isn't it?
Yeah, I mean, it does look heavy-handed, unfortunately. Those were some really... interesting projects like the...
Well, that can douse any train by then, pretty much. At that point, yeah, we just kill Onyxia, reboot, run to Molten Core, and just go all the way to Rag. And we probably just boon before...
Adrenaline from the rain.
What is happening?
You gotta get over that one at some point, bro. You can't be good out on your friends.
All the chocolate wasn't so.
Oh, who's this?
So because you know I'm fat, you just instantly just shit on me. Everybody just shits on me because you know I'm fat.
Tinakoto.
I don't know. Yeah, this way,
Also,
guys.
I don't care that you're fat. I just care that you eat a lot.
Wait, do we have 2 more douses?
Yes, sir. I got one.
Okay, anyone else have
We
one?
just need one more.
Oh, nice. Wait, Puffy just did it, right?
So I'm just jamming in my phone.
So we need one more.
Oh my god, my group's Kiwi, clearly. He's cool. Oh, he's from the guild Only Freaks, bro. Nice.
Alright, guys. Casters, GFPP, mages, spam Greater Fire word. Spam fire word off CD so you don't get one tapped.
The dog is coming down.
Yeah.
You want a reaction
I thought you were just referencing Tyler.
Oh, there's a Surger.
Kiwi living in Spain.
Pull the
Hell yeah.
Surger, we just banish. Banish the Surger. Banish the Surger. Okay, face it away from the raid. Banish, banish. Nice, good. Just watch for the heartbeat on that, okay?
I'll have a look. I'll have a look.
Any healers free to dispel?
Teaching people how to do the haka in Spain. Jesus, that's crazy.
I'll pre-taunt the Surger.
Good work, guys.
I have aggro. This is the furthest one, by the way.
Bro, what the fuck? Can we ban this guy, please? Chat?
Yo, Grayson.
Yo.
He's talking about end game,
Good
obviously,
draft,
but
bro. You're not gonna leave us.
so I got 2-week ban min.
I mean, I think they're having other people every week do like the
This is your raid, bro.
Yo,
You
shit, dog.
want to be a small fish or a big fish racing?
Yeah, none of us want to go to any of the raids now, you know?
Damn. Yeah, I mean, I
They
think
don't
you
want
should
us,
have
we don't
high
want them,
expectations now.
We are the outlaws.
Having the Islander.
Chuck, you ain't even Oni yet, too, bro. You motherfucker.
Listen, man, I just need Ubers, bro. Come on, man.
Pull it out.
Yo,
Yeah,
you
yeah,
got
yeah.
Ubers. Fucking audience with them, shit.
Yeah, because you took a nap, dog, but you do have kids.
Listen, man.
You're a dad.
I go to bed at 6 a.m. Gotta take my little sister to school. Got 3 kids. What'd you do today, Grayson? Walked your fucking fridge, little bro?
Yeah, and you know, said hi to Bean on the couch. Yeah, Raid led a raid, let 2 people down. But honestly, them dying, I'm gonna be honest, not on me. Not on me, boys. I'm not
The
taking
dog
that.
is coming, by the way.
Listen.
Hey, not on me either, actually. True.
Shit.
As a
I'm at the spot where Zico
literal
died.
professional healer who gets played to play this video game, let's hope you let him fucking die, bro.
Oh,
shit, there it is.
Easy pull.
It's because
There
we're
it is.
busy
Stroke.
healing the guy with
Well,
4k
I'm not a
HP, you know?
professional healer.
He wasn't pressing anything. He was not
okay,
stunned,
that's
and he was not
okay.
pressing any levels. Butso definitely murdered him for 100%.
Yo, this
Although
Died
saying
for like
that,
3 seconds, man.
Able to do on this offensive line, but Josh Sweat is the one that's interesting to me. They extended him years ago. Myles Garrett has requested that he wants a trade, and I wonder if Howie Roseman is sitting there thinking, well, we'll get rid of some money. We'll try to get Myles Garrett and continue to build on this defensive line that has been dominant now 2 times in Super Bowl runs.
City on 2 games simultaneously. What do you mean? City is not on 2 games. Wait, who are you telling that? Is Grayson's looking at C2? Who is looking at C2? With the Butso
Can
guy.
GFPP quit?
He's eating again.
I think it's a random variant between like 1950 and 3250 or
Well,
whatever.
my
Guys, don't
GFPP
stand
is
in
like
that, by the way.
5k now.
Make sure you're not facing these mobs. They could insta-stun everyone, okay? Just...
I rebanish Diamond.
Okay, we get square.
Right here.
Okay, diamond's out. We're good.
Burn it.
Yeah, there's another BOE bracers, dude. Kind of crazy.
You need to turn this.
Speaking of eating, you're gonna see some eating, bro. You're gonna see some eating in the documentary, bro. You're gonna see some eating in the documentary that's coming out today. Get your poke chance ready for Professional Gamer 3 coming out today, boys. Coming out today. And once Ragnaros dies,
Like, you guys stay,
or they die,
right now you can
boom,
stay here,
we're posting it.
so you don't
I
get-
believe it's ready to go.
Don't get randomly stunned. I'll pull these. Just banish the,
It's a documentary, literally. Yes, it's a documentary on my gaming lifestyle or something. I don't quite know what the arc is or what. Zach is the creative director.
Okay, Black Magic, you have me up at 4 o'clock in the morning. I don't even have pants. Now, I go to sleep like normal human beings, and sometimes you wake up to use the men's room, or the boys' room, or the person's room, whatever you want to call it. And I decided to look at my phone while I was inside of the bathroom, and one of the things I noticed is Black Magic has an announcement. The Ursa Cine 12K, one camera that was one of the best cinema cameras that I think for the money in 2024, is now half the price. There's a couple of caveats, and they're not gigantic deals, I guess, in my opinion, but well, we'll get there. The Black Magic design announced the Ursa Cine 12K, which they did at NAB last year, but this is a little bit different. Now, the original Ursa Cine 12K came with a bunch of accessories and battery plates and handles and different things to make your production life a bit easier, and having some of the accessories in case you didn't have them for this camera. Now, Black Magic Fashion decided to make that camera that was like $14,000 last year about half of the price. Right now, you can pick up an Ursa Cine 12K for $69.95, but keep in mind there's going to be a couple of caveats. A lot of those accessories that you were used to beforehand, well, you have to kind of get them on your own or get them separately, or you can get them from a third party. If you're someone that has your own top handle, battery plate, shoulder mounts, and all the other bells and whistles that came with the Ursa Cine 12K package, well, then you can save a heck of a lot more money and just buy the body only and start from there. Especially for someone who just wants to get the body design because they're not skipping out on the sensor quality. All the shooting modes that are on the original Ursa Cine 12K are going to be available in this format as well. Just doesn't have all the accessories and all the bells and whistles, which at the same time, for $7,000 less, I'll take that any day of the week. I'm gonna take that like right now. I haven't found a retailer in Canada just yet that sells it immediately, but the second that it's in stores, I might fight people to be in line, which also means that these Pixis days might be numbered. If you guys haven't noticed, I am in the Pixis run. I'm committed to actually making 25 videos of the Black Magic Pixis just because I want to share all the pieces of information that I actually knew before kind of, talking about other cameras, because that's what we do on our channel sometimes. If you're someone who has an Ursa Cine 12K, the Super 35 version, or maybe you have a Pixis yourself, this actually provides a really nice upgrade path, especially if you have all the accessories already. Black Magic reminds you of that crazy guy in a street fight, which you don't want to mess with because even though you think you could win, they're just not going to quit. They're going to keep on fighting. It's insane for a price point that's a little bit more than the Sony FX6, a camera that I used quite quite a bit. It's not only going to have one of the fastest shutter readouts out of any cinema camera, also has one of the highest dynamic ranges out of any cinema camera. It's going to be in a price point under $10,000, which makes me feel even less bad about selling my Red Komodo X to Blackmagic Pixis now. Yes, I'm still petty about that. You guys are very, very upset that I did that. Now, I'm going to reference my phone really quickly for a second because there's a couple of other notes on this Ursa Cine 12K that you can get at a more affordable price. So you're still getting the same sensor. It's still going to be, well, it's going to be lightweight now because you don't have any of the accessories, but you're also going to only have an EF mount. If you want to change out that mount, you can get them separately, or you just get a PL adapter and call it a day. So that's not a big loss there. You're still going to be able to shoot at 12K, 9K, 8K, and 4K for editing. And from what I understand, the way that the sensor works on the Ursa Cine 12K, you don't actually have to crop into the sensor to do that. But also, I could be wrong. I should probably use it a bit more. But from what I understand, you can crop down to 4K and still use the full width of the sensor. You're still going to get an OLPF on the sensor as well because they're not changing anything on the sensor. And you're also going to be able to get higher frame rates. You can shoot at 80 FPS at 12K, 144 FPS at well, at 8K, you can shoot 144 FPS. That's insane. And you can shoot at 240 frames a second at 4K. All of those numbers are insane. I maybe only will use 80 frames a second at any given time, but that's just a lot of frame rates. You're still going to be able to use all of the accessories that you would originally use on the original Ursa Cine 12K, and as well, of course, you're going to still get a free copy of DaVinci Resolve. Now, one accessory that might be a little bit significant, especially dealing with the size of the files coming out of the Ursa Cine 12K LF, is that 8TB module. The original version of this does come with an 8TB module you can insert into the camera, and that way you can offload your footage without having to worry about filling up cards all the time. Now, that doesn't necessarily mean you can't store any data on this camera variant. You're going to have a CF Express type module, which I'm sure is going to be CF Express type B cards, so at least you can store some footage. But I don't really know yet if that's going to affect things that you can shoot in terms of your frame rates and your shooting modes, as CF Express type B cards are going to be different than having essentially an 8TB hard drive installed into your camera. This is a crazy time to be alive as somebody that's into filmmaking, someone who's into cinematography, and you're looking to buy a camera at a relatively affordable price. Typically, this kind of camera, this kind of format and function used to cost almost 10 times as much just a couple of years ago. And now you can get one for $7,000, which I mean, for a lot of people might be a lot of money, but it's also comparatively significantly less than what I expected. Now, question might be, do I think I'm going to get the Ursa Cine 12K? At $7,000, I just might. I already sent my emails to Blackmagic to see if they can maybe get me one, but if not, I'm probably just going to buy it with my own money and cry about it later because I was doing well. I was saving some money. I actually had money for a rainy day. It was like a good amount of money now, but now that's all going to fall apart because Blackmagic made me do it. That being said, if you guys want to check it out, I don't even know if there's like a link on B&H or anything like that yet, but if you want to know more information, because the internet probably knows more things than I do, I'm going to leave a link in the description down below to the article from Blackmagic, and if I find a link somewhere, obviously, if you click on it, I may get a kickback, which I might need because this is going to cost me a lot of money, and I'm kind of here.
Hey there, Jake here from CVP. Today we are taking a look at Blackmagic's latest cinema camera. This is the Ursa Cine 12K, and it's frankly a bit of a statement camera from Blackmagic. It's them showing that they want to be considered as an A camera for more cinematic and controlled productions. And this new Ursa Cine series does have some pretty revolutionary features, so let's dive into this intriguing new cinema camera.
Bro, Zeke was right up at this area. This hive is spawn as fuck.
Bro, just chill for a second. Let me get threat. I can't taunt yet. Watch threat, you freaks.
Bro, who's this?
That's a good ass rotation.
Congrats on the crit, Madness.
Let's go!
Some 3 points.
Alright.
Any Mageblade hypers or something?
Bro, I was saying to kill the dogs. They're immune to damage. What, the mana igniting cord? That's pretty
Dude, that game was crazy, guys. It was great. That's not one of the bosses I ever played on.
Anybody die? What is this caster day?
I think we have to keep healing.
Wait, like, how many prophecies?
Wait, do we douse this pocket? Right over here on the right?
Wait, I can have advantage at level 20, right? What the fuck am I doing?
Best clear, 193 minutes. Bro, we were in there forever the first week. That's insane.
That's a long minutes.
Yo, Star, thank you for the tier 1, dude. Thank you, bro.
Volps, I don't get how your frost bolts hit that hard, man. You're pumping.
Oh, he hits one button. That's nuts.
Dude, Volps is actually OP.
Yeah, are you pressing it hard?
That's crazy. I should press one button.
He has every single buff available.
Okay, someone just carried taunt. Taunt that caster, get it.
Holy shit, you're running Supreme Power. You're a mad lad.
Yeah, good shit.
How much HP do you have, Bobs?
Why don't you let the fat guy play for you?
Yeah, he has been all
He
right.
seems better than you.
Whoa, dude.
1,100 less than everybody else.
I mean, they have Fire Ward and shit too, an Ice Barrier.
It's kind of based.
Kind of hot.
Morning show, and
I won't be watching.
I'll let you.
Yeah,
I'll
what
keep
Severance
letting
is to
know.
you is
Yeah.
the morning show to me.
But this was more enjoyable. I think she looks fantastic. By the way, I was literally like Reese Witherspoon, like age, workout, whatever.
Yeah.
Like, what do I have to
It's called
do?
the substance, man.
Well, she looks, like appropriate. Like, she looks her age-ish, but like the best version of her
Sure,
age.
she's a multi-millionaire.
I do understand that. I understand she has access to treatments and resources that I do not.
Some dark arts, perhaps.
She's using them prudently.
She looks great.
Yeah.
Neither of us saw the movie Love Hurts, which is another movie that technically qualifies for this, but I had just been told by a great number of people it is not very good.
Right.
And I'm looking at the reviews. This is the new film.
You kill Logan.
And I misclick my ice block. When I ice block the fact that he says I'm shaking and I'm trembling and I misclick my ice block, when I ice block the fucking debuff that drains my mana so I can continue to do damage, I mean, it's like watching a bronze player try to backseat Faker. It is what it is. Out of everyone in that raid, I had the best positioning. I was the only one who stood at a spot where you can't get hit by the fucking Inferno, even if the boss is tanked in the worst spot possible. And I still had to move because the boss was so fucking close that it moved out of line of sight. And you can ask any classic sweat about that.